Welcome friends to my YouTube channel Sommo Physics. Yesterday I told about artificial satellite and natural satellites, and also I derive an expression for orbital velocity and time period of revolution of an artificial satellite, and I also discuss the case if the satellite is very close to Earth's surface. Now in today's lecture I will discuss about a special type of satellite which is called geostationary satellite. So let's proceed. Now first question that arises, what is geostationary satellite? Now it is an artificial satellite for which the orbit must be circular. Okay, the first condition is that the orbit must be circular. Orbit must be circular, and the satellite revolves around the earth with same velocity as earth does about its own axis. Okay, the satellite revolves around the earth revolves around the earth with same velocity as earth does about its own axis. Okay, so if a artificial satellite satisfy these two conditions, if a artificial satellite satisfy these two conditions, that is the orbit is circular and the satellite revolves around the earth with same velocity as earth does about its own axis, then the corresponding artificial satellite is called geostationary satellite. Okay, corresponding artificial satellite is called the geostationary satellite. Now we have to find out the orbital velocity and time period of revolution of a geostationary satellite, and the procedure is same as we did before. Now we consider Earth. Suppose the geostationary satellite is located at a height h from Earth's surface, that is this is h. Okay, and if this is the center of Earth, then this is r. Now if the geostationary satellite is located at a height h from Earth's surface, then the total distance from the center of Earth is r plus h, which we called small r. So what will be the force of attraction between the geostationary satellite and the Earth? We all know that force of attraction will be g into mass of Earth, that is capital M, and mass of geostationary satellite, that is mg upon r square. This is the force of attraction between the Earth and the geostationary satellite. And we all know that for any circular motion there must be a centrifugal force. Okay, so what will be the centrifugal force due to the rotation of the geostationary satellite? That is mg into v square by r, where v is the orbital velocity of the geostationary satellite. Okay, orbital velocity of the geostationary satellite. Now we all know the orbital stability condition. That is, the stability condition is what? Stability condition is what? Stability condition is what? These two forces are equal. That means centrifugal force, this is equal to force of attraction, gravitational force of attraction. Now if we equate this, what we get? We get v square, this equals to gm upon r. Okay, So again we all know that G equals to Gm by r square at the surface of Earth. So we can write Gm as G into capital R square by small r. Now what will be my velocity? That is r into square root G by r. So we see that orbital velocity is independent of the mass of the geostationary satellite, because there is no term mg. Mg is absent here. So it is independent of the mass. Okay. Independent of mass. Okay, it independent of mass. Okay, of the satellite. Again how we find out the time period of revolution? We all know that time period of revolution, that is the circumference of the orbit by velocity. Now what will be my v? My v will be this. So if we substitute, we get this expression. Now if we take square, then what we get? 4 pi square into r square into r by capital R square G. Okay. Now from which we can write t square, this is equal to 4 pi square by r square into r cube by G. Now they are all constants, that is 4 pi capital R G, these are all constants. So we can write t square is proportional to r cube. So again we see that a geostationary satellite also obey Kepler's law of planetary motion, Kepler's third law, that is t square proportional to r cube. Okay. Now we have seen that the time period t square can be written as 4 pi square r cube by G into capital R square. Okay. Now from which we can easily calculate r. How we can? That is r cube, this is equal to G into r square t square by 4 pi square. Now what will be my r? My r will be G into r square t square divided by 4 pi square whole to the power 1/3. Now if we put the values of different quantities, then what will be the value of r? So if we substitute G 9.8 meter per second square, if we take capital R, this is equal to this into 10 cube meter, and if we take t, that is 24 hours, that means 24 multiplied by this second. Okay. So if we substitute all these values, then r will become approximately 42,400 kilometer. Okay. If we put these values, then this will become this. Okay. So we get r. Now again we know that small r, this is equal to capital R plus h. So my small h will be r minus r. So this is, if we substitute the value of capital R, then this. So ultimately this. So there we see that a geostationary satellite must be placed at a height 36,000 kilometer from Earth's surface so that it can work properly. So a geostationary satellite must be placed at a height 36,000 kilometer from Earth's surface so that it can work properly. Okay. So it is a very important question. So this is the answer, that h equals to 36,000 kilometer. Now one question, that what are the uses of geostationary satellites, or you can say what are the uses of satellites? Now what are the common uses? We all know. First of all, these satellites are used in GPS, that is global positioning system, and in navigation system, and they are also used in navigation system and GPS. This is one of the common use. And another use is that in weather forecasting, they are used in weather they are used in weather forecasting. Okay, and also these satellites are used in phone calls and satellite televisions. Phone calls and satellite televisions. Satellite televisions. And another important use is that they are also used to track storm and pollutions. Storm and pollution tracking. Okay, storm and pollution tracking. So these are the common uses of an artificial satellite that we all know. First of all, they are used in global positioning system and in navigation system. They are used in weather forecasting, or they can be used in satellite television and phone calls, and they are used to track storms and pollutions. Okay, so these are the common uses of artificial satellites. Okay, now in our next class I will discuss about the binding energy of an artificial satellite, binding energy of an artificial satellite, and weightlessness in an artificial satellite. Okay, so today we have discussed about the geostationary satellite, and we see that a geostationary satellite must be placed at a height 36,000 kilometer from earth's surface. Okay, and we also talk about few uses of artificial satellites. Okay, so if you don't subscribe my channel, kindly subscribe it and share it to your friends. Okay, thank you.